Oh, the Inspire, it won't be called that in the Inspire. These are names I made up. That's what I was telling Dave. We'll figure this out. At break, we'll sit down and figure out how to get what you need to get. Okay? It'll take a little, they won't be programs, they'll be built-ins. I have to find them in your machine. That's all. Okay? Okay, so I just gave you guys, there's only 2 programs we'll need today, maybe a third one by the end of the day. We'll see how that goes. But in order to get the distribution we need, you have to go to the program PRGM button, which is under stat, PRGM. And when you get in here, kill one of these lights. Yeah, that'll work. There's a whole bunch of stuff, a lot of which is 244, some of which is 105. But dist fill stands for distribution fill, and because I didn't know what else to call it, I had 8 letters. So dist fill is the one you want. Press enter on it, then press enter again to run it. You have to know something about your variables before you start filling your distribution though. So for example, you have to know what x is. I mean, the TI will fill it, which is fine. What are we interested in this experiment? What's x going to be if I watch Max 10 times? Jen?
Times he gets it right and wrong.
Exactly. Let's just pick one of those. How about right? Yeah, x is going to be the number of times Max, Max gets the Crocs on the correct feet. If you can think of this, it's like he's flipping a coin, but you're unsure about the probability that he's flipping it on. Just like the chickens. The chickens were like flipping a coin too. It's a coin that lands heads up 90% of the time. It's not a normal coin. I think I told you the story. What Max wanted to do was he wanted to bring the chicken home from his school. They hatched a chicken at school. And they just got these random fertilized eggs and they hatched them at school and a bunch of them hatched. Can we bring them home? I'm like, no. He's like, why? I'm like, because it's more, I think he had 4 at school. Because the most likely outcome for 4 randomly selected chickens is 2 boys and 2 girls. Because those are coin flips. Those aren't sexed. They were done and got into the school while they were still in the egg. The sexing process for day-olds happens after they're born. So they come out of the eggs, they're 50-50, they're boys and they're girls. And they lift the skirt, they check, and they say, okay, you're a girl, you go over here, girl, girl, you're a boy, 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 and then the girls go to the store, and the boys, I think, go to Lizard Man, down at the lizard store, I think, I'm not sure. But he wanted to bring them home from the school. I said, no, dude, I don't want a binomial with an average of 0.5, 50%, I want 90% from the store. Does that make sense? So the question is, what distribution is Max behaving with his shoes? Is he 50%? Is he 90? Is he 10? I don't know. Let's assume he's guessing. Omar, yeah?
Did Max really understand the statistics behind that?
No, he didn't. My wife did, though. Because she wanted to bring her home, too. I'm like, babe, she got it. She totally got it. Because actually, I flipped coins with Max to illustrate it, but he still didn't get it. That's when she got it, though. She's like, oh, okay, I got it. Please.
When you chose his name, were you thinking Max Rule?
Like a superhero? Totally. Yeah. It's just Max. It's not Max and Mr. Max. It's just Max.
I just kind of realized that because I wrote his name and wrote his last
Max
name down.
Rule.
Like,
It's going to be a superhero if he does it already.
Yeah.
I gave him a middle name of Benjamin just to soften him a little bit. Max Benjamin. I wanted an X in his name, and Max just seemed perfect.
Sorry.
Yes, I did. yes, I did. So, speaking of Max's superhero rollers Crocs, what's the least number of times he can get his shoes on the correct feet? He might not at all, so 0 is going to be the smallest. Press enter. What's the most number of times he can do it? Lydia, ask me that question.
Mine looks different. It says smallest 0, question mark again. Am I still for 0?
We may have, let's follow it through, see if it works. We may have corrupted it. I can overwrite it again at the break, no problem. If it doesn't work. What's the most number of times? The largest X?
10.
10. He might get it correct all 10 times. Fair enough? Beautiful. When you press enter, right now, if you were to stop the program and looked at L1, L1 would go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It would keep track of all of the individual components that make up this probability distribution, as far as the X values go. Now you've got to tell the TI what goes in L2, which are the probabilities. And this one is binomial. So pick number 1. And now you have to tell it, okay, I know it's binomial. What probability are you assuming Max is using? At this point, we're assuming he's using 50-50.5. I'm assuming he's guessing. When I see shoes on the wrong feet sometimes and don't see them other times, I just assume that some kind of guessing is going on. Fair enough? Fair enough, good. So 0.5. Make sure you put it in as a decimal. That's how I've coded the program to work as a decimal. Okay, look. Press enter. It takes a couple seconds and it says done, which is very, very boring. I know, it's exceptionally boring. If you want to look at the distribution, you can go back and look at it now by pressing stat edit. And the entire distribution is in there. L3, your L3 should be blank, I'm assuming. So it looks something like this. So let's assume Max is guessing. Let's assume Max is guessing. What is the chance he never gets his Crocs on the correct feet? Basically 0. 0.00098, which is 0.0001, which is 1 in 10,000. In other words, he probably won't ever have that happen if you're assuming that he is guessing. If you're assuming he's guessing, even if he's guessing, he's not going to get it wrong every single time except for 1 in 10,000 trials. And you got to remember what that means, 1 in 10,000 trials. It means I watch him 10 times, 10,000 times. In one of those 10,000 times, he doesn't get the shoes on the correct feet at all, 10 times, all 10 times. Yeah, Lydia. We'll fix it at the break. We'll fix it at the break. Follow with me right now. What's the chance he gets them on the correct feet 1 time and screws it up 9 times? That's about 1 in 100, right? That's about a 1%. If I round that up, it's about a 1% chance. So if I watch this experiment 100 times, he's one of those times he'll get the shoes on the correct feet 1 time and he'll screw it up 9 times. That's what that means. It's pretty unlikely, yeah? Pretty unlikely. How about 2 times correct, 3 times wrong? 4.3%? Still pretty small. Still pretty small because he's guessing, right? If he's truly guessing, what should he average as far as the correct number of times? What should he average 50% of the time, which will be 5 out of 10? Go look at 5. 5 corresponds to the highest probability. In other words, if I repeat this experiment over and over and over again, roughly 25% of the time, he should get the shoes on the correct feet half the time. Which means out of every 4 times I watch him, 10 times, one of those 4, he's going to have 5 and 5. One of those 4, he's going to have 5 and 5. Would it be unusual? Would it be unusual for him to get it right 4 times and wrong 6 times? Is that unusual? 21%-ish? That's pretty big. That's like 1 in 5. That's not rare. How about 3 and 7? 12%? That's 1 in 8. This is within the realm of possibility if he's guessing, yes? So if he got him 3 times and didn't get it 7 times, that's still going to happen 1 out of 8 times. That doesn't strike me as like, that's weird. When they start getting small, that's when it strikes me as weird. Or when they start getting... What do you notice about those numbers down here? Oh my goodness, does that make sense? Should the probability of getting them right 10 times be the same probability as getting them wrong 10 times? Why? Because the probability was 50-50. It's just like flipping a coin. Getting 10 heads on 10 coin flips is just as likely as getting 10 tails, assuming the coin is equally weighted 50-50. This is different than getting 10 chickens or getting 10 roosters, because that's not equally weighted 50-50. But this, everybody do this real quick. Do this real quick. Press program and go to dist draw. I think we messed around with this a little bit in class on Thursday. Go to dist draw and just press enter and then hit enter again to make it run. That's the graph of Max guessing. Here's the chance he never gets it right out of 10. Once out of 10, twice out of 10, 3 times out of 10, 4 times out of 10, 5 times out of 10, 6 times out of 10, 7 times out of 10, 8, 9, and 10 times out of 10. What does that look like? Looks like a bell curve, doesn't it? More on that to come. More on that a little bit later. But yeah, it's a symmetric. If this was chickens, watch this, don't change yours. I'm going to change mine real quick. Program, dist fill. If this were chickens and not my son, it would look like this. That's still 0 to 10. I bought 10 birds, but it's not 50-50 anymore, right? It's 90-10. That's why the curve shifted to this side. If it were 10-90, it would look like that. Makes perfectly symmetric, one or the other. But what's nice about testing versus guessing, this is a very useful strategy we're using here. If I do dist fill 0 to 10 with a 0.5 probability, and then I draw it, what's nice about this is this beautiful symmetric curve allows us to test the effect of an experiment. In this case, the effect of what Max thinks. So, we already answered a question, right? The question we answered was, on average, how many times should he get the shoes on the correct feet? And we said, half the time, which would be how many times out of 10? 5. I'm sorry, I'm going like this to give you the answer, I apologize. What would the plus or minus be on that, do you think? Can you tell by this curve what the plus or minus would be? I haven't done this in a while with you guys, and I want to come back to it now because it'll actually help us in this next 2 weeks together. If you had to approximate, that's definitely the average, right? I'm going to call that mu. Mu's 5. Mu's 5. For sure, the average is 5. Can you approximate what the plus or minus is? Ish, ballpark it. So here we'll go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
5 plus or minus.
Plus or minus 5. Why 5? Well, 5 would go all the way down to 0 and 10.
Yeah.
Could it be 5? On average? I don't think it could be 5. I think 5 is too big. And because remember what standard deviation is. Standard deviation is, on average, how far away the data points are. 5 would be saying that the extremes are average.
Plus or minus 3.
Plus or minus 3? I think that makes that's a little closer, I think, for the plus or minus 3.
2.5.
2.5. 2. Remember when we did, I could be drawing back too far in the past. We set up where 95% looked like it was before. Remember doing that back in the day? It's been a while, I apologize, bastard move actually. We kind of did something like this, where we said that's about 95% of the data, and then we said that's about 2 standard deviations, and then we cut it in half to make 1. You're not remembering this. It's okay.
Yeah, so
Forget
then
it.
it would be about 1.5 then?
Good, so 1.5, 2, 2.5, somewhere in that neighborhood. I guess what I'm getting at here is, if you don't want to approximate it, it sounds like you don't want to, that's totally fine. You don't have to. You have the distribution in your machine, right? So what can you run?
1
1
bar.
bar stem.
Yes, don't ever forget you can do that. You can do 1 bar stats, just make sure you do it on L1 and L2, because it's a weighted average. And when you press enter, look at that, you guys are damn good. The average comes out of 5. Gesundheit. Gesundheit, you're welcome. And the standard deviation is about 1.6. Damn close, you guys, 1.5 and 2. Very, very nice, very, very nice. We'll come back to that whole approximation next week. I do want to bring that back. It was too early to do it right now. I think I have to talk about the bell curve some more. We haven't talked about it enough recently. So if you needed to know it, if you needed to know what that plus or minus was, it looks like it's about 1.6-ish, around. Fair enough? Now, I'm going to give you 2 slides here really quickly, and you can go back and look at it if you want to. There are formulas for these. The average and the standard deviation have formulas. For example, if you needed to know the average, the formula, and you guys figured this out last week, you take the number of trials times the probability of success, n times p. 10 times 0.5 is 5. So you actually figured that out with the chickens. You realized that every single time you add a chicken, you add 0.9 of a girl. So when I had 4 birds in my flock, 4 times 0.9 is 3.6. You had that figured out from day 1 almost. Fantastic. What you might not have had figured out is the standard deviation actually has a formula as well. It's nowhere near as neat and clean as the average. It's this, if you ever need this. It depends. If you take 244 with Donna, she likes formulas a lot more than I do. That's awesome, I love formulas too. The thing I don't like about this one, check out, this is how you calculate it. N times P times Q. So N is the sample size, 10. P is the chance of success, 0.5. Q is the chance of failure, which is the other 0.5. Exactly, so it'd be 10 divided by 4, which is 2.5. Square root of 2.5 is the 1.6 that we got up here. Now, when I first saw that, and don't memorize this, please don't memorize this, okay? When I first saw that, I asked my professor, Dr. Mason, I'm like, Dr. Mason, what does that mean? He's like, what do you mean, what does it mean? I'm like, I know what the standard deviation means, but how does that work? Like, how is that equal to the standard deviation? He's like, what do you mean? I'm like, okay. So every standard deviation we've done in this class since Bert and Ernie has been done in the machine. But the reason we've done it in the machine was because we learned how to do it manually back in the day, which was take each data point, subtract the average, square it, multiply it by its weight, add them all up, take the square root. That was, I mean, we did that with Bert and Ernie back, it's been like 8 weeks now. How is that equal to that? He goes, what do you mean? I'm like, okay, we're not getting through to each other here. So what I did was I took it home, and I actually worked it all out. If you guys are interested, I'll show you real quick. If you're interested to know, as I was, where that formula comes from, I want to tell you about this real quick. You might not know this page exists. If you go to the enrichment page of the website, there's a whole bunch of stuff down here. There's a whole bunch of stuff down here. And a lot of the things about, like right here, the mean and standard deviation of the binomial, if you're interested, or if you need to fall asleep sometime, this is my response to myself when Dr. Mason wouldn't answer my question. This explains why, and you see it down here at the very bottom, there it is right there, NPQ equals it squared, take the square root, square root of NPQ. If you need to pass out some night, you need some sleep, you can't get to sleep, just try reading this for about 5.5 seconds. Mathematically, it does work out. It does work out. Just wanted you to know, if you ever need the formulas, they're here in this spreadsheet, they're here in this PowerPoint. I'm not sure where you're going next if you even need them. I like using technology to generate the things. You have one of our stats, we use it all along. But just that the binomial does have slick little formulas that go along with it. But the problem with the formulas is they include what we're actually trying to figure out, which is what? What was the point of this whole experiment?
Whether it's on accident or...
Right! Whether Max is guessing when he puts his Crocs on, or whether he thinks that that is the correct way to put them on. Now, Trey just gave us more evidence over there. He said he watched kids at the pool over the weekend and he saw a whole bunch of 2 through 5-year-olds with the damn shoes on the wrong feet, which is interesting to me. So, I never told you the conclusion of my experiment, which is this. In those